In the previous video, we discussed problem 1, and problem 1 is about normal approximation. We use the normal approximation to estimate confidence intervals and confidence bound. Let's look at 1.2 a little bit more closely. We use 95% as our confidence level, but what if I change this problem to something else? Instead of 95%, let's use, how about 90% confidence interval? In that case, what do we get? Well, the initial picture will change a little bit. Instead of 95%, the middle should be only 90%. Did you notice the change? The middle part became 90% and left hand side 5%, right hand side 5%. As we change, the blue point moved a little bit to the right, red point moved a little bit to the left, and this middle, the confidence interval, got a little bit smaller. Because 90% is basically the area underneath this curve. So that got smaller, so the confidence interval got smaller. So what happens here? The margin of error also got smaller, as a matter of fact. If I estimate the mean computing time is 42.6, then what is the maximum error within this confidence interval? Well, with 90% of chance, the true mean will fall from blue to red. And the maximum error I'm going to make is right at the end point in the red point or blue point. That difference will be associated to this 90% confidence level. Let's see, how do we actually find it? The same thing, z is approximately speaking end minus center over standard error, so standard deviation over square root of sample size. Let me expand the font. And that is associated to the z-score for the 5% here. What is z-score for the 5%? We did it already. It was negative 1.645, yes, right here. Negative 1.64, 0.0505, negative 1.65, 0.0495. So let's estimate it as negative 1.645. And solving that equation, you can get our x value. In this case, if you solve that, x will be approximately 42.6 minus, font is too big, 1.645 times 16.7 over square root 2500. If you calculate this thing, we're gonna get about, well, something like this. That is left hand side endpoint. Right hand side endpoint will be, well, pretty much the same, except that you have to go to the right. So change the sign. And we have, well, appropriate number right here. Okay, I'll estimate kind of like this. using the same idea, z equals to n minus center over sd over square root of n, and then appropriate z-score, just an algebraic process, and then just symmetry, and that's how you get the confidence interval. Now what if I change this into larger confidence level? Instead of 90%, what if I change this to say 97%? Bigger than 95? Okay, what do you expect? Bigger confidence interval or smaller confidence interval this time? Larger confidence interval. Consequently, bigger margin of error. So if I predict as a center, the biggest error you can get within the confidence interval is right at the endpoint. So that's going to get bigger. Now, instead of negative 1.645, this time you'll have to look up, let's see, 1.5%. Middle is 97% this time. Let's look up 1.5%, 1.5% right here. Negative 2.17. So that's going to replace negative 1.645, so 2.17. And this is 2.17. And that's 2.17. And calculate these endpoints out. 41 point something. So definitely smaller. And if this is plus 43 point something, 3.3, again definitely larger. And here we are, these are 1.86 and this is 3.2. Okay, there goes our confidence interval if we have 97% there. What conclusion can we draw? The change of confidence level affects the size of confidence interval. The bigger the confidence level, the bigger the confidence interval, and the bigger the margin of error, basically. Here's another adjustment you can think of. Instead of 2,500, let's take smaller sample size. The sample size is just 500. What difference will it make? In terms of picture, you're not going to see anything actually. We have 97% here, 1.5% here, 1.5% here, 42.6 here. But what is x1 and what is x2? They're going to be affected this time. How are they affected? Well, here's a computation. Instead of 2,500, they're changing to just 500. Let's see. What if we calculate these? Instead of 41 point something, 40.97, significantly smaller. Now, what about the red point? 44 point something, significantly larger. So the confidence interval is 40.97 to 44.22. What happened here? Confidence level got big. Confidence level stays at 97%, excuse me, but sample size became smaller as a consequence, confidence interval got larger. And you can see that kind of behavior from the endpoint problem here. And this is center, this is z-score, standard deviation, square root of n, and that changes. The bigger denominator, that means smaller overall value. So we are subtracting smaller number in the end. And vice versa, if you have smaller sample size, that's how we have these inverse relationship. The smaller the sample size, the bigger the confidence interval, and consequently the bigger the margin of error. Error is going to be 42.6 all the way to the endpoint here. So the radius of this interval, the half of this interval size, is a margin of error. One more thing you can consider is changing the standard deviation. If you change standard deviation 16.7 into something different, like for example, change this into say 10.7, how do you think will these numbers change? It'll get, this will get smaller. Okay, got larger, excuse me, because we subtracted something smaller. And then this one got smaller because we added something smaller. Consequently, we got smaller confidence interval. So what kind of conclusion did we draw from this kind of experiment? Let's try to summarize that. Being all other things equal, if we get larger confidence level, what do we get? Larger confidence interval, and that leads to larger margin of error. Now, being all things equal, larger sample size, smaller confidence interval, and consequently we get smaller margin of error. Eventually your approximation is becoming better if you take larger sample size. If you take larger standard deviation, you cannot just take it, excuse me, if you assume standard deviation is larger, then what happens? Larger confidence interval, and consequently larger margin of error. That's what you're gonna get, being all other things equal. That's what we learned from those kind of tweaking by adjusting those quantities.